All right, let's talk about p-threads. You know, if you've ever wondered how to really make your computer fly by getting your programs to do a bunch of things at the same time, you're in the right place. We're about to unlock a serious superpower.
So here's a plan. We are not just going to throw a bunch of theory at you. No, today is all about the journey. We're going to write a program together, from scratch. Then we're going to watch it break in some pretty interesting ways. And then we're going to figure out how to fix it step by step.
I mean, this is really the core question, isn't it? Why do one thing at a time when you could be doing tons of things at once? Most of our computers have multiple cores these days. It's like having multiple brains ready to get to work. So why would we ever force them to stand in a single file line, tackling tasks one by one?
And this slide just nails the concept. On the left, you've got the sequential way. It's like one cashier at a supermarket with a super long line. It gets the job done, eventually, but on the right, that's parallel. We've opened up a bunch of new checkout lanes. Since each of these calculations is totally independent, there's no reason to wait. We can just do them all at the same time. Bam! It's a massive speed boost.
Now, you've got options for how to do this. There's a tool called OpenMP, which is fantastic. It's high level, it does a lot of the heavy lifting for you. But today, we're rolling up our sleeves and using p-threads. And the reason is one word: control. P-threads gives us direct, low-level, granular control. Yeah, it's a bit more work for us, but it is the absolute best way to really understand what's going on under the hood.
Okay, enough talk. Time to get our hands dirty. We're going to start with a core function called pthread_create. Just think of it like this. Our main program is the parent, and pthread_create is the command it uses to spin up a new child worker, or thread, to go off and handle a specific job.
So here it is, our first program. Pretty simple. In our main function, we create a variable for our thread, child1. Then we call pthread_create. That's the magic moment. We're telling it, hey, create this new thread, child1, no special attributes, and have it run the function myfunc1. And what does myfunc1 do? It just prints hello world. Right after creating the thread, our main program prints no more children, and then it exits. So, what do you think's going to happen?
And the output is no more children. That's it. The program ran, it finished, but our hello world message is just gone. What on earth happened?
So this is our very first bug, and it's a classic, a real rite of passage in multi-threaded programming. We know we created the child thread, but we never actually saw it do its job. So, why not? Here's the deal. It was a race to the exit. Think of pthread_create as firing a starting pistol. Our main program fired the pistol for the child thread to start running, but then it immediately sprinted to its own finish line, that exit 0 call. The main program finished and shut everything down before our poor child thread even had a chance to get off the starting blocks.
So how do we fix this? Well, luckily, the solution is really elegant. It's a function called pthread_join. You can basically think of it as the parent thread putting its foot down and saying, hey, I am not moving another inch until my child1, comes back and reports that its job is done. It literally blocks the main thread and forces it to wait.
And just look at how simple the fix is. In this new version, we're creating two children. Right after we create them, we just add a pthread_join call for each one. That tells the main thread, okay, stop right here. Wait for child1 to finish. Done? Great. Now wait for child2 to finish. And only after both of those children have completed their tasks will the main thread move on and print its own message. That's it. Our race to the exit is solved. Okay, problem 1, down. That's awesome. But things are about to get a whole lot more interesting. Because what happens when our threads aren't just working independently in their own little worlds? What if they need to access and change the exact same piece of information? Let's see what happens. So, we've upped the ante. We've got 4 threads, and all of them are trying to update the same single counter variable. We want them to print their messages in order, right? Job 1, then 2, then 3, but just look at the output we get. It's a complete mess. Job 2 finishes before job 3 even starts. The order is totally random and unpredictable. This is pure chaos. This chaos actually has a name. It's called a race condition. Imagine 2 of us trying to update a number on a whiteboard. I look at the board and see the number 5. In my head, I add 1 to get 6. But right before I can write 6 on the board, you look at it and you also see 5. You add 1 and write 6. Then I finally write my 6 over yours. We both did an increment, but the final number is 6, not 7.
That's a race condition. The result is just plain wrong because it all depends on the unpredictable timing of who did what when.
So, how do we fix this mess? We need a traffic cop. And in pthreads, our traffic cop is called a mutex. It stands for mutual exclusion, which is a fancy way of saying one at a time, please. A mutex is basically a lock. Think of your shared data, like our counter, as being inside a tiny room that only fits one person. To get in, a thread has to grab the one and only key. If another thread comes along and the key is gone, too bad. It has to wait outside until the first thread is done and puts the key back.
Now, using a mutex isn't a free-for-all. There's a strict 4-step dance you have to do every single time. First, you initialize it. Step 2, right before you touch that shared data, you lock it. This is you putting the Do Not Disturb sign on the door. Step 3, and this is absolutely critical, as soon as you are done, you unlock it. And finally, when you're completely finished with it, you destroy it to free up resources. Init, lock, unlock, destroy. You can't forget a single step. Okay, let's look at the code. See that part in the middle where we're messing with the counter? That is our critical section. It's the danger zone. And notice how we've wrapped it or protected it. We put a call to pthread_mutex lock right before we enter and a call to pthread_mutex unlock right after we leave. Now it's impossible for more than one thread to be running that block of code at the same time.
And the result of that small change? Look at this. It's beautiful. Perfect, predictable, sequential order. The chaos is completely gone. Job 1 starts and finishes its business entirely before Job 2 is even allowed to get the key. Our mutex worked. It has tamed the race condition.
Awesome. We did it. We're done, right? Well, not so fast. Because this powerful new tool, the mutex, introduces a brand new and very dangerous type of problem. What happens if a thread locks the door but forgets to leave the key for the next person in line?
So here's our program again, but this time I went in and I just commented out that single pthread mutex unlock line. Watch the output. Job 1 is started, Job 1 is finished, and then nothing. The program just hangs, it's frozen, stuck forever. This catastrophic failure has a name, deadlock. What happened is our first thread grabbed the key, went into the room, did its work, and then left, but it took the key with it. So now you have all the other threads just lined up outside the door, waiting patiently for a key that is never, ever going to come back. They will wait forever, and our program is effectively dead.
So, this means using mutexes requires some serious discipline. Here are the golden rules. First, and this is the big one, always unlock what you lock. Forgetting is how you get a deadlock. Second, keep the time you spend inside that critical section as short as humanly possible. The longer you hold the lock, the more time other threads are just sitting around doing nothing. And finally, if you're ever juggling multiple locks, make sure every thread locks and unlocks them in the exact same order to avoid really nasty, complex deadlocks.
We have been on quite a journey today, haven't we? We've seen how to create threads, how to wait for them, how to use mutexes to protect our shared data, and maybe most importantly, how to avoid shooting ourselves in the foot with a deadlock. We've learned how to control the chaos. So the only question left is, now that you have this power, what amazing problems are you going to solve with it? Thanks for tuning in.